back again, and this time I want to discuss about Hadoop processing. In my last session, I discussed about big data and Hadoop storage. And in this one, we would discuss just about Hadoop processing. So what is Hadoop processing? Hadoop processing means the process or the method or the flow it takes to process the dataset that we stored in our Hadoop cluster or Hadoop distributed file system. To explain you the complete flow of Hadoop processing, I need to draw the complete architecture and flow of Hadoop. So let's get started and let me show you in a diagram. And before we go through the flow of Hadoop processing, I would like to recap the Hadoop storage again, how we would store the data in HDFS, and then we will see the complete Hadoop processing. So let us start and let me draw quickly a Hadoop cluster. This is node 1. Or rather I should say now data node 1, data node 2, data node 3, data node 4, and so on. And now these data nodes are connected to a master machine that's called name node. And assuming I have a dataset of 1 GB, approximately equal to 1000 MB, and let's assume we have block size of 64 MB, and for simplicity let's keep the replication factor equal to 1. Okay, so now since I have 1 GB of a data set, let's divide into 64 MB blocks, which comes around 15.6 or something, and it will take 16 blocks. Even though it is coming around 15 point something, 15 blocks will have complete 64 MB of data, and the remaining 0.6 will take complete one block, because block is the smallest container to store the Hadoop data. So in total, to store 1 GB of data, I will take 16 blocks. So let's see how it will store B1, B2, B3, B4. You may again start at B5, B6, B7, B8, and so on. So now the data is stored in our data nodes in the form of blocks, and each block is independent of each other. Okay, so this happens automatically and taken care by framework. As soon as you put your data in Hadoop cluster, it will be automatically split into blocks and stored on data nodes. And now this is a kind of storage diagram, and as we understand, if the data is stored in a distributed manner, the processing will definitely happen in distributed manner, right? So, and in master machine, this is our master machine, and as I told before, this name node is a kind of daemon service running in a background, or it's a Java application running in a background. Similarly, we have the master and slave architecture for storing the data. Similarly, we have the master and slave architecture for processing too, and the master process or daemon is called job tracker. This is daemon for, or I should say master daemon for processing. And in this slave node, I have task tracker. And all these things like data node, task tracker, these are actually daemons or background process or a Java application running in the background. And on the basis of these daemon names, these are named as nodes. Now, and there is actually one more kind of node in Hadoop cluster that's called secondary name node. And I didn't talk about secondary name node even in my last session because this needs a kind of separate kind of discussion and it's not related to our topic. But just to give a idea about what is secondary name node so that you have complete understanding of Hadoop cluster, this is not a backup of name node. This is a kind of false name given to secondary name node and it looks like a backup node, but it's really not a backup node. This is a kind of helper node which is processing intensive. Like I told in last session, name node is a RAM intensive machine. Secondary name node is a processing intensive machine and helps to keep checkpoint of name node or the changes in metadata happening at name node. So this is just a helper node and helping the name node. So now I won't talk much about secondary name node. It needs more detailed discussion. And when I combine all these things, that makes a complete Hadoop cluster. So now in total, I have 5 kind of different daemons running in my Hadoop cluster. Name node, master service, which takes care of all the blocks and the files stored in the data node. Job tracker, it's a daemon service, master daemon service that takes care of all the task tracker running in the cluster. And then we have a data node which actually store the data. Then we have a task tracker, which is a kind of, again, the processing unit that takes care in locally in that particular node. And then we have a secondary name node that takes care of checkpointing the name node metadata. So now we need to see how the processing takes place. And before we start the processing, we need to understand, like, since we divided the data in each block and each block is independent of each other, similarly the processing will happen on each block separately. So a separate processing will happen on block 1, separate processing will happen on block 5, separate processing in block 2, block 6, so that it is distributed evenly in the form of blocks and coincide with how we have stored the data and take the full power of distributed storage and distributed processing. So now let's get started. Let me clean it up and draw you a little clear picture so that it's better and you can see the screen better. So now I have name node, job tracker, and these are my data node 1, job tracker 1, data node 2, job tracker 2, data node 3, job tracker 3. Now here is my client which submits the program to job tracker. And now we need to understand this client is your local machine from which you are submitting the job to the Hadoop cluster. Okay, and this program is running in client JVM. And when I say JVM, it's a Java virtual machine. It's a kind of computing machine that is needed and needs to be loaded in memory to run any Java program. And as we know, we right now, like all these processes are Java application or Java services running in the background. And we are also submitting a Java program. So this client machine running JVM, and it runs or submits a Java program to the job tracker. Now, once the job is submitted to a job tracker, it is having a long queue. And this queue has a list of, let's say, job 1, or I should say master job 1, master job 2, master job 3, and so on. What are these master job 1, 2, and 3? Since it's a Hadoop cluster and you are not only the one client submitting your job, there may be other clients, C2, C3, C4, those are submitting and using the cluster at the same time. So all these jobs are taken into queue. Considering the job I just submitted is master job 1, job submitted by client 2, master job 2, 3, and so on. So this cluster is being shared across many clients. So it puts the job in a queue, and on basis of some priority or on some algorithm, it will take one job to execute because it needs to make some priority. So on the basis of priority, let's say it picks up the master job 1 or our job that we just submitted. Okay, and this job tracker is also running in a separate JVM. And this task tracker is also running in a separate JVM. And data node is also running in a separate JVM. Same with all. Every one is running in a separate name node, running in separate JVM. All these are Java applications. Okay. And why we have separate JVMs? Because if something happens to, like, let's say one JVM and the program stops suddenly, we don't want to interrupt the service of others. So we have separate JVM for everyone. So now we have a job and we picked up the master job 1. And similarly, we have a task tracker running here, task tracker running here, task tracker running here. So as soon as it will pick up the job 1, okay, and this job 1 will be executed on some data. Okay, and we already stored 1 GB of data here, B1, B2, B3, B4, or B5, or B6. Okay, we already have the 1 GB of a data set stored in our cluster, and we are executing some program on this data set or on these blocks. Job tracker will first contact the name node. Why? It will contact the name node to get the block locations where the data set is actually stored, because the job tracker needs to know what are the location of blocks for these files. And on the basis of this location, once it identifies, okay, the data is stored on data node 1, data node 2, and 3, let's say our entire 1 GB data set stored across this one, then it will pass the task to only these 3 nodes, not to any other. Even though if there are other data nodes, let's say data node 4, and it doesn't store any block related to our data set, it will not assign any task to this node. Why it is so? Now we need to see on a separate note. Now, traditionally, what we were doing, traditionally, if this is your application and you have a data, then data was flowing to the application. Data will go to the job or the application and the process will happen. But if you see, the size of your data is very large in almost every case, and the code size is very small in any program, because you know your program may be hundred of line or thousands of line, but still it will go in, let's say, in MBs or KBs, but the data is definitely of very large size. So traditionally what we are doing, we are moving the data to the code, but Hadoop said, why we are moving data to the code, why not we move code to the data and pass the computing to the data, because it takes me very less resources and less network bandwidth, right? Because now you are moving data, so it's just a few KBs or MBs of data is actually moving to the data which we want to process. So code is moving. So same thing is happening here. Since Hadoop believes in moving the computing to the data, it moves the Java code to each data node. It will give a separate copy of Java code to each data node to execute the job on the local copy of the block. It will not send the Java code to the node where I have no blocks. By this property, this is called locality, data locality, which means I am processing my data on the same machine where my data is actually stored, right? Because I am not passing the processing here and my data is stored here. I am passing the code on the same machine where my block is actually stored, and this gives me a data locatability profit, and I really don't need to move my data, and computing code is going to each data node separately. So this is a very important concept we need to understand about the data locality. Now, in task tracker, so in job, it divided the job into multiple tasks depending on, let's say, 3 machines having the data. It will, and on the basis of also, like, the task tracker should be free to execute. If task tracker is not free, then master job will wait for task tracker to be free because my data is stored here. And how the job tracker will get to know? The task tracker communicates or send beats frequently with the job tracker in a similar way what data node was doing with the name node. So it constantly communicates with the task tracker, is it free, not free, or if task is moving, system logs or other logs, so that once the job tracker gets the log, like, okay, 10% complete, 20% of completion, it passes the same kind of message to the client machine. So now till point we are clear, like we have data stored, and now we are going to assign tasks to the task tracker on the basis of availability. Assuming in our case all 3 task trackers are free, then it will assign the tasks to the task tracker. And also I'm assuming all my 1 GB dataset blocks stored in these 3 blocks, on 3 nodes only. Okay. And as I told, task tracker is running in a separate JVM process. Okay. And in a task tracker, again, we have 2 kind of slots, map slot and reduce slot. And by default, this has 2 map slots and 2 reduce slot. This is configurable. In one data node, In one task tracker, we have two slots for map task processing and two tasks for reduce slot. What is this map reduce? So map reduce is a programming model to process the Hadoop data. Okay, this is a programming model, not a language. When I say model, it means in whatever language I am writing my MapReduce program, I need to follow some procedure or some algorithm to compliant with that model. So the Hadoop uses a MapReduce model to process the data set stored in our Hadoop cluster. So that's a kind of like program divided into two parts. I am not going to talk about MapReduce in more detail since it needs more detailed session to discuss about MapReduce, but in a short, the Java program that we submitted consists of map and reduce tasks. So now we have two map tasks and two reduce tasks. So, and one map task executed on one block at a time. One map task will only take one block. Second map task will take second block. And once it's free, then again we have two map slots free. Then again it will start from next block and so on. So at any point of time, one map task will be working on only one block. Clear? Okay. Now next. Now we need to understand when the task is assigned to the task tracker, and we know there are two types of tasks in a Hadoop cluster: map task and reduced task based on our programming model. Now when the request comes to task tracker, again it will launch a new JVM to execute one map task. So separate JVM or map instance to process one particular block of data. So assuming if this map task is working on block 1, then it will spawn separate JVM. And same goes with the reduced task. So if I have two map slots, then I am working with two JVM. Why we have separate JVM for task tracker and why we have separate JVM for two separate map instances? There is a reason for that. Because if you try to execute your map task in a task tracker JVM, and if something goes wrong in a map task and it throws an exception and my JVM terminates, then it will terminate the task tracker JVM itself, which we don't want because task tracker is working on other tasks as well. Similarly, if I have two map slots, right, I could spawn only one JVM with two threads to work on two map tasks. We are not doing because we want each task to be executed separately and should not be affecting the exception of one into other. Clear? This is also very important that task tracker doesn't execute the task in its own JVM, whereas it creates a child JVM or child instance to execute the map and reduce task. So now one block working on map task, similar will happen in next node, similar will happen in next, and same will every node. And as soon as, let's say, if this node finish the two map tasks, it will report back to the task tracker that okay, I am free and I have two map slots open for next task. And again, job tracker will assign the next map task of same job, or it may pick up the next job also. It again depends, like if it's more job in a queue and how the task tracker is free or not. And while task tracker is executing the map task instance will be communicating with the task tracker for the status and system log and everything about the completion or in progress. And same it will pass to the job tracker how it is running or not, and same will pass to the client. So next, now this processing is also fault tolerant. How it makes fault tolerant? When task tracker submits the job, when job tracker submits the job to the task tracker and map and reduce task executing, and if any map tasks fails due to some exception, it will report to task tracker, it will go to job tracker, and then depending upon the issue, it will relaunch the task on same node or on some other node, and it will try to relaunch it 3 times before it really terminates the GVM and returns back to the user or the client. This is how it takes care of re-executing the task in case of any error. If it's like some temporary error, then next time it will be executed. And there is one more term that is also very important in this execution. When this job tracker submits a task to the task tracker and this one is taking little longer than other task tracker job, let's say other task tracker jobs finish in 1 minute and this one is taking or will take 5 minutes, then we have output from all the task tracker, only one task tracker output is pending, then it's really delaying the processing of entire data set, which job tracker doesn't want. So if one task tracker is taking longer than expected, then it will relaunch the same task to the other nodes having the replication of that block. And when it relaunches, so let's say if it finishes this task in 2 minutes, then it will take into consideration of output of this one and discard the output of this one when it comes back after 5 minutes, or vice versa. Like if it may take 6 or 7 minutes and this output come first, then it will accept the input of this one and discard the output of this one, and this thing is called speculative execution in Hadoop framework. So I guess this is all how the processing takes place in Hadoop framework, and in coming videos I may be discussing about the secondary name node, which I didn't discuss, and then we may discuss about the map reduce model as well. So that's all for today. Thanks for watching my video. If you like it, then please comment, and if you have any questions, then don't forget to drop me an email. Thank you.